Here we have a capacitor with the dielectric medium inserted in between here. Now the question is, first of all, why do we need a dielectric medium inside a capacitor? So in the beginning we discussed that the capacitor is a device that is used to store the charge, and we want that there should be a device that stores the charge at a low potential. We want to have a device which stores a large amount of charge at a very low potential. Now look, if we do the formula of capacitance is Q divided by V. If I somehow can decrease the potential, then its capacitance will increase. It means this device will now store the same charge at a low potential. That is the purpose of our capacitor. And first we discussed that we were having a spherical capacitor, and in the spherical capacitor we were having the constraint of the geometry. We need to increase the geometry, then only we can increase the potential. But here, using the two parallel plates, we can decrease the potential to the significant amount, and then we can store the charge. But still we want to increase the capacitance, so what we can do is we can put a dielectric medium in between, and this is how it will look like in a practical life. So this is the dielectric plate, this is also a dielectric plate, and these are the two parallel plates of this parallel plate capacitor. So if you insert, somehow it will decrease the potential, and because of that there will be increase in the capacitance. So now, how to calculate the new capacitance? We want to find out the new capacitance. So here I am, just for the calculation I am taking some values. So let's assume that the area of this plate is A. I am assuming that area of this plate is A, and the distance between the positive and the negative plate is D. Distance between plates is D, and the thickness of the dielectric medium, or this slab, is D. Thickness of slab is okay. Let us also assume the charge on the positive plate or the negative plate is Q. Charge on plate is Q. Alright. Now look, this charge will be uniformly distributed on this plate, so there will be a charge density, and that charge density is sigma is equals to Q divided by total surface area of this plate. Okay, now because there is this positive plate and this is a dielectric medium, so this dielectric medium will have some induction, and because of this induction there will be the negative charge in the left hand side and the positive charge in the right hand side, and because of there will be some electric field. Now we know the relation of the electric field in a medium and in a vacuum. So in the vacuum, if the electric field is EV, then electric field in the medium is EV divided by epsilon R, or the EV divided by, here we will use the dielectric constant K. So the dielectric constant and the relative permittivity are the same thing. So the K will be given in the question, and K will be greater than 1. So what will happen? This electric field in the medium will decrease. Now what is the electric field in the vacuum or inside the parallel plate when there is vacuum? We have done this calculation in the previous video. So if you don't know this calculation, you can watch the previous video. We have done the calculation for the EV. The electric field in the vacuum comes out to be electric field due to the positive plate, which is sigma divided by 2 epsilon naught, and plus the electric field due to the negative plate, sigma divided by 2 epsilon naught. And why we are writing? Because the electric field at the midpoint of this capacitor is in the same direction, that's why sigma divided by 2 epsilon naught plus sigma divided by 2 epsilon naught, that comes out to be sigma divided by epsilon naught. This is the electric field inside the vacuum. So then what is the electric field inside this dielectric medium? E medium is sigma divided by K epsilon naught. Now why we are doing this calculation is that because we want to calculate the capacitance in this condition, and the capacitance is Q divided by V. So we want to find out the V so that we can calculate the capacitance. Okay, so to calculate the V, or the potential difference between the plate, we are going to use the relation dV is equals to negative of E vector dot dr vector, where E is the electric field and dr is the direction vector. So here we can take this total space between the plates. Okay, let me just again draw it. Here we have this first plate, and this is our second plate. This is our first plate. Okay, and here is our dielectric medium in between. So let me give the points. This is our first point, this is our second point, third point and fourth point. So between point 1 to point 2 in this space we have vacuum. This is our vacuum. This is a dielectric medium between point 2 to point 3, and point 3 to point 4 is our again vacuum. So if you want to find out the potential difference between plate 1 and 4, the point 1 and 4, we need to do the integration from 1 to 4. So the total potential difference will be minus of ER vector dot DR vector from point 1 to point 4. Now I can, because I have different function of the electric field for the space 1 to 2, 2 to 3 and 3 to 4. So I will break this total integration into the three parts. So negative, and then we have integration from 1 to 2 E vacuum dot dr vector, then plus integration 2 to 3 E medium dot dr vector, and then we have the integration 3 to 4 E vacuum, again that is vacuum, multiplied by dr vector. So our total potential difference will be minus bracket. Here E vacuum is sigma divided by epsilon naught. We know this, right? So this is sigma divided by epsilon naught. This is also sigma divided by epsilon naught. So we can take out the constant from the integration, right? So sigma divided by epsilon naught, and then we have integration from 1 to 2 dr, and then plus integration 3 to 4 dr, and then we have this 2 to 3. So the electric field inside the medium is E sigma divided by k epsilon naught. So sigma divided by k epsilon naught, and integration 2 to 3 dr. Okay, we got this much. Then the potential difference is negative of sigma divided by epsilon naught, and this total dr vector 1 to 2 and 3 to 4, look here, the total distance, this distance is d and this thickness is t. So remaining distance between 1 to 2 plus 3 to 4 is d minus t, isn't it? So this is our d minus t, and then we have sigma divided by k epsilon naught, and what is the integration of the dr 2 to 3? dt. So here we have the potential difference del v is equals to minus sigma divided by epsilon naught, we can take out common, and then we have d minus t plus t by k. So again we can simplify this potential difference. So the potential difference will be minus sigma divided by epsilon naught in bracket d minus t, we can take out common. So then here we will have 1, and the next term we will have minus 1 by k, because we have taken the minus t common. This is our potential difference. Now what is the capacitance? We will use the capacitance formula, C equals to Q divided by V. So C is equals to Q divided by V. Q is the charge, which can be written down as sigma multiplied by A, divided by V is the potential difference. Let's put the positive value. So sigma divided by epsilon naught D minus T 1 minus 1 by K. Now look, sigma and sigma will be cancelled out. So it means this capacitance is the property, and it should be independent of the charge, and it is independent of the charge from here, and we are getting epsilon naught A divided by D minus T 1 minus 1 by K. This is our expression for the new capacitance when we insert a dielectric slab inside the capacitor. Now what is the effect of the different factors? Let's look here. What is the effect if I increase the dielectric constant? If I increase the dielectric constant, look here, 1 by k value will decrease. So this value, total value 1 minus 1 by k, 1 minus 1 by k value will increase. Total value 1 minus 1 by k will increase, and the total value d minus t 1 minus 1 by k will decrease, and because of that the capacitance will increase. So in total, if I am increasing the k, what is the effect on the capacitance? It is increasing. Okay, what if I increase the thickness of this capacitor, dielectric slab? If I increase the thickness of this dielectric slab, so if I increase the thickness of this dielectric slab, then this value, negative value d minus t 1 minus 1 by k, because this is a negative value, this will increase, and in total this value will decrease, and because of that again the capacitance will increase. Okay, so this is the effect. What if I fill this capacitor fully, completely with this dielectric medium? So if the capacitor is filled completely with the dielectric medium, then in this case the capacitance will be C equals to Q divided by V, and that is epsilon naught A divided by D. And now the thickness of this dielectric slab is equal to the distance between the plates of the capacitor, so D 1 minus 1 by K. If we further simplify it, we are getting epsilon naught A divided by D minus D minus minus plus D by K. That becomes K epsilon naught A divided by D. Look, interestingly, this epsilon naught A divided by D, we have done the derivation previously. This was the capacitance in the vacuum. So can I say that C of medium, when the medium is fully filled inside the capacitors, both of the plates, is K times of C vacuum. So this is a very interesting expression which we are getting over here. So we have done the all the related derivation related to the capacitance and when we fill the medium inside it. Now there may be some questions related to this dielectric slab. What if I pull this dielectric slab? So what will happen if I pull it a bit and release it? Will it go inside? Will it perform the SHM? Will it perform the oscillations, or it will come out? Okay, the next question may be, what is the charge on this dielectric slab? Because there is induction, so what is the charge on this dielectric slab? How this dielectric slab will affect the stored energy inside this capacitor? So all these questions we will be dealing in the next video. In this video, what we have discussed is very important. We have done the new formula. We have derived the new formula for the capacitance, which is epsilon naught A divided by D minus D 1 minus 1 by K. This is a important formula, and we used this dV equals to minus E vector dot dr vector for the derivation. And okay, we have also done the derivation of the electric field inside the medium, which is EV divided by K. This is an important relation. Okay, so that's all for this video.